effect that is relevant to your design, you can throw that in here. And that could be corrosion, for instance. If you know that, if you've studied the product that you're manufacturing and it is in a corrosive environment, and so you want to take that into account, and you can do that by specifying your own endurance limit modifying factor. Residual stresses would be another one that you could account for here. Does everybody get the concept of these endurance limit modifying factors? Yes, there's a question in the back.
So is there like a quantitative endurance limit factor, or is it just...
No, oh, I'm not suggesting to make stuff up here, right? I mean, this needs to be done in a quantitative way, obviously. You have to somehow quantify the effect that hasn't been accounted for in these other parameters, and then account for it in a quantitative way in that new parameter that you're defining. Or not just like ballparking or something. I mean, I guess you could, but that would not be a good way of doing engineering, right? Does everybody get this concept where we transform sigma E prime, which is the endurance limit of our Moore specimen, to the endurance limit of our actual mechanical element by multiplying it with a series of factors, where each of those factors accounts for one specific difference between the Moore specimen and the actual mechanical element. Is that clear to everyone? Okay, so then we're going to do an example problem that is going to allow us to practice that in addition to still in the context of doing these fatigue calculations, right? So we're going to calculate, of course, here these endurance limit modifying factors in addition to doing a fatigue strength problem. So we're going to use an AISI 1080 hot rolled cantilever beam. Alright, this is the cantilever beam. Cantilever beam is 0.6 meters long. There is a load acting on its end, and that load F is equal to 2000 sinus omega t. And then the cross section of this cantilever beam is square. With side B. And the question is as follows. Design B. If this cantilever beam must support this load. For 10 to the power 4 cycles. With a design factor of 1.5. Is that problem clear to everyone? We have this cantilever beam, right? Attached to a wall, there's an alternating load acting on it, F, perfectly reversing. It's a sinusoid. The cross-section of that cantilever beam is a square of side B, and the question is if this entire setup needs to work for 10 to the power 4 cycles with a design factor of 1.5, what is B? Yeah. Say that again? Yes, newtons. Okay? So let's solve this problem. A good way to start any of these problems is starting from your design factor, right? So what are we eventually going to calculate? Well, our design factor is equal to the loss of function parameter divided by the maximum value of that parameter occurring in our design. So in this case, what is going to be our loss of function?
Sigma max.
Sigma F, right? The fatigue strength. In particular, the fatigue strength at 10 to the power 4 cycles. Remember, we said we can't really talk about a fatigue strength unless we specify how many cycles we're talking about. And then what is the maximum value of the stress occurring in our design? Well, that's going to be some type of alternating stress component, sigma A, that we'll have to calculate. Now, sigma F, we learned how to calculate last time, right? It's going to be a function of that parameter A and parameter B. And that in itself is going to be a function of our material properties, sigma E, the fatigue strength fraction. So we'll have to go through all of that. And then sigma A, what is sigma A going to be a function of? What kind of loading do we have here? Bending, right? Is this simple bending or is this a combined loading case? Simple bending, right? There's no other loading. So we can calculate sigma A using the Flexure formula, right? So that's going to be the bending moment times the maximum distance from the neutral axis divided by the moment of inertia of this cross section. And so you can see that this is going to be a function of our bending moment, which we'll be able to calculate. We know the force, we know the leverage arm. The maximum distance from the neutral line we can calculate too. That's going to be b over 2. And then the moment of inertia we can calculate too because we have the geometry. The only problem is it's going to be dependent on B, right? So that sigma A is going to be dependent on B. And so that's going to be our unknown because we know what the design factor is. We're going to be able to calculate this. And then sigma A is going to be a function of B. And so we'll eventually have to solve for B. That's sort of the idea behind the solution methodology that we're going to follow. Yes?
So when we have sigma F as our failure,
Speak up, because people in the back need to be able to hear you too.
when we have our failure criterion as sigma F, is the denominator always going to be sigma F?
Yes, because you need to have, well, but I mean, I call this sigma A because this is going to be, I want to make clear that this is an alternating stress component. And yes, since sigma F is an alternating or a dynamic stress, you can't compare a dynamic stress component to a static stress component. They need to match up. Okay. Yeah?
When you're calculating sigma A, do you use the equivalent that you calculated in your...
We'll get to that. Yeah, we'll have to use a D equivalent, right? Because this is not neither a rotating nor a circular beam. Right? Other questions before we start? Does everybody get the methodology that we're kind of going to follow? So we'll have to calculate sigma F, we'll have to calculate sigma A. So we'll start by calculating sigma F. And so let's go in our formula sheet to the calculation of sigma F. All right, sigma F is A times n to the power B. So we'll have to calculate A and B, and then we can calculate sigma F. And to calculate A and B, we first need to know our mechanical properties of the material, and then from that we can calculate sigma E, the endurance limit. So, we're dealing with AISI 1080 hot rolled steel. You can look that up in your table. believe it's table 820, and then you can get your mechanical properties, and so sigma UT is 770 megapascal, and I'm also going to write it in kpsi here, because we're going to need kpsi for that table that is halfway visible there for our fatigue strength fraction, and so that is 112 kpsi, and then the yield stress from the table is 420 megapascal. When we start calculating a fatigue failure problem, the first thing we're going to do is always calculate sigma E prime, because we certainly will need that. And sigma E prime is half of the ultimate tensile strength as long as the ultimate tensile strength is smaller than 1400 megapascal, which is the case here. So we have 0.5 times sigma UT is what? 350 plus 35, 385 megapascal. That's not going to be the endurance limit of our mechanical element. This would be the endurance limit of a Morse specimen made out of 1080 hot rolled steel. Of course, we're not dealing with a Morse specimen, we're dealing with a square cantilever beam here, so we'll have to convert sigma E prime to sigma E. And we do that by calculating the endurance limit modifying factors. We don't have to calculate endurance limit modifying factors for which we have no information. Since, for instance, there's no temperature given here, we're going to say Kd is equal to 1. We have no information, right? Same for reliability or any of these other ones. If we have no information, we set it equal to 1. Let's go to the table of Ka. So Ka is A times sigma ut to the power b, where sigma ut has to be inputted in megapascal, as is shown in the table here. And we have hot rolled. We don't specify how that hot rolled steel is further machined or changed into the square beam that we have. So the only information about the surface quality we have here is that it is hot rolled. So that's what we're going to use. In this case, that means that our factor A is going to be 57.7, and the exponent is going to be minus 0.718. So we can now use that in this equation. Remember, we have to input the sigma ut in megapascal, so this is going to be 57.7 times 770 to the power minus 0.718. And that is equal to 0.488. So right here, we already cut sigma E in half. And it's a huge effect of that surface factor by just having hot rolled rather than polished. That cuts your endurance limit in half. KB, the geometry factor. Obviously, there is a geometry effect here, right? It's not a nice Morse specimen. In fact, it's not even rotating. It's a square cantilever beam. So we'll have to calculate an equivalent diameter and then plug that value into our equations that are shown here and calculate KB. The only problem is we can't calculate our equivalent diameter because the very factor that we need to calculate the equivalent is our unknown, right? So there's two things that we could do. We could drag the equivalent as a function of b throughout our entire calculation and probably end up with a higher order polynomial in the end that we need to solve for. Because if you drag that b and then that b is going to go into your stress calculation later, and so that's going to be a difficult problem to solve. The easier approach is to assume a value, and then when we're done with our calculation, let's come back and check whether we made a good assumption or not, and if not, then we'll have to adjust it and recalculate. But it's going to be an easier calculation to do. So that's what we're going to do. We don't know b. In fact, that's the very parameter that we're trying to design for, so we can't calculate kb. So we're going to make an assumption for kb, And a good assumption to make for KB is that it is equal to 0.85. That's a good initial assumption. And what we'll then do is we'll design B, solve for B, and then once we have a value for B, we can calculate the equivalent diameter, and then from the equivalent diameter we can calculate the KB factor, and we can compare that KB factor to the value that we have assumed. If we find out that this actual KB factor is lower than the factor that we have assumed, then we'll have to recalculate. If we find out that it is larger than the factor that we have assumed, that means we were conservative in our assumption, and we probably won't need to recalculate. Yes?
You guessed your 0.85. What was your reason for guessing that?
Well, the reason that I take 0.85 is experience, because I've done this before, but I'm telling you, and because I know the outcome, and we don't have time to do an iteration, and so this is probably going to be very close to what we're going to find in the end. But what I'm telling you here, and this is the important message here, I'm telling you that 0.85 is a good assumption to make if you don't know what KB is, right? And not just in the context of doing academic problems on here in this course, but also in doing actual calculations, right? So if you don't know, take 0.85, but check afterwards. I mean, that's key. Don't just make an assumption. You have to make an assumption and then check whether that assumption was actually correct, right? So.
Question.
Yes.
Is that only if you're using metric units?
The 0.85?
Yes.
No, it is ultimately you should find the same KB factor whether you say if you have a 20 millimeter shaft and you convert it to inches and you plug it into this formula, or you plug 20 millimeters into this formula, you should find the same KB factor, the same physical problem, right?
Okay, cool.
Okay, so we don't have any other information about KC. Well, KC, the loading, is it's pure bending, so we're going to take 1 for KC, and then KD, KF, KE, we have no information. So we're going to say sigma E is equal to KA times KB times sigma E prime, and so that is 0.488 times 0.85 times sigma E prime was 385, and so that is 160 megapascal. Okay, now we can calculate the fatigue strength, because we have sigma E, which is what we need to calculate our fatigue strength. We can calculate these two coefficients, A and B. The only parameter that we still need is F, the fatigue strength fraction. So let's write that one down too, and then we're done with that. So our fatigue strength fraction is a function of the ultimate tensile strength, and in that table it's given in kpsi. We have 112 kpsi, so if you go up this vertical line here, it must be somewhere between 0.82 and 0.84, so let's take it equal to 0.83.